In episode 57, titled Power Planning, Voltage, Wattage, Amperage, PDUs, UPS Essentials, the point is to treat power as the uptime foundation for network and compute gear rather than as a facility's afterthought. Networks can be beautifully redundant at the routing and switching layers and still fail if the power design is careless. The exam tests this topic because power problems are one of the most common causes of everything went down at once, and because power planning requires you to connect basic electrical concepts to practical infrastructure decisions. You do not need to be an electrician to reason about power correctly, but you do need a clear mental model of what voltage, amperage, and wattage represent, and how they relate to capacity and safety. Power distribution units and uninterruptible power supplies are also core building blocks in rack design, and the exam expects you to know what they contribute and what they do not. This episode builds the foundational understanding you can use to prevent breaker trips, avoid false redundancy, and size power buffers realistically. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Voltage is best understood as electrical pressure, and amperage is the current draw, meaning the amount of electrical flow a device pulls through a circuit. Electrical pressure describes the potential that pushes current through a circuit, while current draw describes how much current is actually moving. This distinction matters because circuits are rated for a maximum current, and exceeding that rating trips breakers or creates unsafe conditions. In practical terms, when you add equipment to a rack, you are increasing current draw on a circuit, and that is what determines whether you are approaching the circuit's limit. The exam often expects you to recognize that voltage is a property of the supply, while amperage is what changes as load changes. It also expects you to know that current draw is what you monitor and manage to avoid overload. When you understand voltage and amperage this way, you can connect equipment load to circuit capacity without confusion. Wattage is the actual load that drives heat and capacity planning because it represents real power consumption rather than potential or flow alone. Conceptually, wattage is the work being done, and it is closely tied to how much heat the device produces, which matters for cooling and rack density decisions. Wattage is also the number that equipment specifications often provide for maximum draw, typical draw, and sometimes power supply sizing. When you plan rack power, wattage helps you estimate how much energy is being converted to useful work and heat, and it helps you compare different devices' impact on your power budget. The exam often tests that you understand wattage as the practical measure of load because it influences both electrical capacity and thermal capacity. A rack that is within amperage limits can still run hot and unstable if the wattage is high and cooling is insufficient. Power planning therefore ties directly into heat management and uptime because overheating can cause throttling, failure, or emergency shutdowns. When you think in wattage, you are thinking in real consumption and real operational impact. Power distribution units, often called PDUs, distribute power within racks and enable monitoring so you can see what is actually being drawn. A PDU is essentially the rack-level power strip, but in enterprise designs, it is more than a simple outlet strip because it may support metering, remote control, and circuit-level visibility. Distribution matters because a rack contains many devices, and you need an orderly and safe way to provide power to each device without ad hoc extension cords and overloaded outlets. Monitoring matters because nameplate ratings are not the same as real-time draw, And the only way to know whether you are approaching capacity is to measure actual usage. Metered PDUs can show you current draw and sometimes wattage per outlet or per bank, which supports both troubleshooting and capacity planning. The exam expects you to recognize that PDUs help both with distribution and with visibility, which are separate but complementary roles. They also support operational discipline, such as ensuring devices are connected according to redundancy plans and that power usage is tracked over time. A well-managed PDU setup reduces surprises and prevents incremental additions from quietly pushing a circuit over its safe limit. An uninterruptible power supply, often called a UPS, provides short-term runtime and clean power, meaning it buffers devices through brief outages and helps smooth power fluctuations. Short-term runtime is the key phrase because most rack-level UPS systems are designed to bridge gaps, not to power a full data center indefinitely. Clean power refers to conditioning and stabilization that can protect equipment from voltage dips, spikes, and transient disturbances that can cause reboots or hardware stress. A UPS can also provide time for generators to start or time for systems to shut down gracefully if longer power loss occurs. The exam often tests that you understand the UPS is a buffer, not a generator, and that its value is in preventing sudden dropouts and providing controlled response time. UPS systems also often provide alerting, monitoring, and managed shutdown integration, which are important operational features. When power blips occur, a UPS can be the difference between a seamless continuation and a cascading reboot that takes down network paths and compute clusters. The essential idea is that a UPS buys time and stability, not long-term independence from the grid. To use these components effectively, you must calculate load with headroom so you prevent breaker trips and avoid running circuits at their limit. Headroom means you plan for more than the expected steady-state draw, accounting for peak draw, power supply inefficiency, and future growth. Many devices have startup surges or variable draw under load, and designing to a circuit's exact rating leaves no margin for those changes. Headroom also supports operational flexibility because you can add a device or handle a temporary increase without immediately exceeding safe limits. The exam expects you to understand that a breaker trip is a form of outage and that it is often self-inflicted through overloading. Calculating load is therefore a risk control, not merely an accounting exercise. It also ties into redundancy, because when one circuit fails and load shifts to another, the remaining circuit must have capacity to handle the shifted draw. When you plan with headroom, you are planning for failure behavior as well as normal operation. Dual power supplies are a common resilience feature in enterprise gear, and they only provide true redundancy when each supply is connected to separate circuits. The idea is that if one circuit or one PDU fails, the device remains powered by the other supply. If both supplies are connected to the same circuit, the redundancy is an illusion because a single breaker trip or PDU failure can still take down the device. Separate circuits ideally means separate power paths, such as separate power distribution units and separate upstream feeds, so that a single failure does not remove both. In a rack, this usually means connecting one supply to an A-side PDU and the other supply to a B-side PDU, where A and B are backed by independent circuits. The exam tests this because it is a common real-world mistake to plug both supplies into the closest available outlets, which defeats the whole purpose. True redundancy must be independent, and power supplies are only half the story if the upstream power path is shared. When you connect supplies correctly, you reduce correlated power failure risk dramatically. A scenario that makes power planning concrete is when adding new gear exceeds the rack power budget, even though there appears to be physical space for the device. A rack can have open units and open ports and still be full from a power perspective, because circuit limits and cooling limits are often reached before space is. When a team adds a new switch, wireless controller, or server, the incremental wattage and current draw can push the rack over its safe operating envelope. The failure mode can be immediate, such as a breaker trip, or gradual, such as overheating as cooling struggles with increased heat load. This is why rack planning must track power budgets and not just physical layout. The exam may describe a deployment where adding a device causes instability or repeated breaker trips, and the correct diagnosis is exceeding power capacity rather than a network configuration issue. The right response is to reassess load, redistribute devices across circuits or racks, or increase power capacity with proper engineering rather than ad hoc fixes. Power budgets are constraints that shape architecture. A common pitfall is confusing UPS capacity with long runtime during an outage, leading teams to assume they can ride out extended power failures without a generator or without a planned shutdown. UPS capacity is often expressed in terms of apparent power ratings and battery runtime under a given load, and runtime drops significantly as load increases. A UPS that provides many minutes at a light load may provide only a few minutes at a heavy load, and in real events, those minutes disappear quickly. The exam tests this pitfall by describing a UPS in place and asking whether long outages are covered, and the correct reasoning is that a UPS is a short-term buffer. If the goal is hours of runtime, you need a different strategy, such as generator support, load shedding, or moving critical services to sites with longer backup power capability. Another subtle issue is that UPS batteries age and capacity declines, so relying on nameplate runtime without testing is risky. A UPS that is not maintained can fail to deliver even its intended short buffer time. The key is to plan runtime based on measured load and realistic battery performance, not on optimistic assumptions. Another pitfall is plugging both power supplies into the same PDU, which creates a single point of failure at the PDU and circuit level. This mistake often happens because it feels tidy and convenient, but it undermines redundancy exactly when it is needed. If that PDU fails, if its upstream circuit trips, or if someone accidentally powers it down, the device loses all power at once. In environments with many devices, this can create cascading failures because multiple, redundant devices may share the same PDU, turning one failure into a rack-wide outage. The exam tests this because it is a classic example of redundancy that exists only on paper. Correct power planning requires you to map each supply to a different power path and to verify that those paths are actually independent upstream. When you see dual supplies, you should immediately think about where each cord goes and what it shares. Redundancy is not the number of supplies, it is the independence of supply paths. Quick wins for improving power reliability include labeling circuits, monitoring draw, and testing UPS alarms so teams know when they are running close to limits or when the buffer is compromised. Labeling circuits reduces human error during maintenance and makes it clear which outlets map to which power paths, preventing accidental consolidation that defeats redundancy. Monitoring draw helps detect gradual creep as devices are added or as workloads increase, and it provides early warning before breaker trips occur. Testing UPS alarms validates that the alerting path works, that batteries are healthy, and that the organization will actually notice when the UPS is running on battery. These actions are simple but high impact because they turn power planning into a visible, managed part of operations. The exam often rewards answers that include monitoring and testing because they show awareness that power systems are dynamic and degrade over time. Power issues are often discovered only after failure, and quick wins are about shifting discovery earlier. When you adopt these practices, power becomes less mysterious and less likely to cause surprise outages. A useful memory anchor is volts, amps, watts, distribute, buffer, monitor, because it ties the electrical concepts to the operational components. Volts reminds you of electrical pressure and the supply characteristic that frames the circuit. Amps reminds you of current draw and the breaker limit you must respect to avoid trips. Watts reminds you of real load and heat, which drives both capacity planning and cooling needs. Distribute points to PDUs and the importance of organized, visible power delivery within racks. Buffer points to the UPS and its role in providing short-term runtime and stabilizing power quality. Monitor reminds you that measurement and alerting are how you prevent slow creep and catch battery or circuit issues before they become outages. This anchor is useful on the exam because it keeps you from mixing up concepts and helps you connect them to the right infrastructure elements. When you can walk through the anchor, you can explain both the theory and the practice of rack power planning. To apply these ideas, imagine planning power for switches and wireless controllers in a rack where uptime is critical and maintenance must not cause accidental outages. You would start by estimating the wattage draw of each device under expected load, then translate that into current draw relative to the circuit rating, leaving headroom for peaks and growth. You would use PDUs to distribute power cleanly and to provide monitoring at the rack level so you can see draw by bank and catch imbalances early. For devices with dual power supplies, you would connect each supply to separate PDUs that are backed by separate circuits, ensuring that a single PDU failure does not remove the device. You would place a UPS appropriately so that critical network gear can ride through short interruptions and remain stable during power disturbances, while recognizing that runtime is limited and must be sized based on measured load. You would also plan for how alarms will be detected and how the organization responds if the UPS goes on battery. The exam expects you to connect these steps into a coherent plan rather than treating each component in isolation. When you can describe how the rack stays powered during both normal operation and a single circuit failure, you demonstrate power planning competence. To close episode 57, titled Power Planning, Voltage, Wattage, Amperage, PDUs, UPS Essentials, the essentials are that power is a core dependency and must be planned with the same rigor as network paths and device redundancy. Voltage represents electrical pressure. Amperage represents current draw that must stay within breaker limits, and wattage represents real load that drives heat and capacity planning. PDUs distribute power within racks and enable monitoring that prevents incremental growth from quietly exceeding limits. UPS systems provide short-term runtime and clean power, buying time during brief outages and stabilizing equipment, but they are not long runtime solutions by themselves. Load calculations must include headroom to prevent breaker trips, and dual power supplies only provide redundancy when connected to separate circuits and PDUs. The most common mistakes are overestimating UPS runtime and defeating redundancy by plugging both supplies into the same PDU. Your rehearsal assignment is a rack power planning rehearsal where you narrate one rack's power design, stating expected wattage, how headroom is preserved, how dual supplies are separated, and what the UPS is expected to cover, because that narration is how you turn power theory into uptime reality. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.